Hey everyone, Mrs. Basega here, and today we're working on the Unit 8 Magnetism review. To start off, we're looking at a few different vocab words related to magnetism and the types of magnetic fields, and maybe this image from earlier in the unit will help. When we're talking about a ferromagnet, we could also call this a permanent magnet or a bar magnet. All of those are going to be synonyms. So a permanent magnet, this is a magnet in which the domains are lined up so that we get a north pole. In this case, I would put a material that has most of its magnetic domains aligned in the same direction with permanent magnet. Whereas an electromagnet is a magnet that runs on current. Instead of electrons spinning, we have electrons flowing to create a field. This comes in two different types, either a solenoid or a current-carrying wire. But in either case, the thing they have in common is its electric current creating magnetic fields. So an electromagnet then would be a magnetic field caused by electric current. A non-magnetic material is a material that can't be made into a ferromagnet. This is something like carbon or nitrogen or water. It's a material that has all of its electron spins paired, so the magnetic field for each atom is zero. A good picture to have in the back of your head for this is something like carbon. Carbon has 6 electrons in its outer shells. However, carbon's electrons all cancel each other out. So carbon is not something that can become a ferromagnet. Its spins have canceled each other out. So they can't form domains. The domains can't line up, and so you can't have a ferromagnet or permanent magnet. Now, a material that has domains, but not necessarily alignment of those domains, is called a ferromagnetic material. So let's drag that one down. This is something like iron, nickel, or cobalt, in which it has domains because it has unpaired electrons. The most common form of iron, for instance, has 4 unpaired electrons, so each individual iron atom acts like a mini magnet. Iron doesn't have to be aligned in its natural state, so a ferromagnetic material like iron will have domains, but won't necessarily have the alignment. So what is a domain then? A domain is a microscopic section of a ferromagnetic material in which all the electron spins, or most of the electron spins, are aligned with each other. That leaves electromagnetic induction, the only concept that's not currently on this screen. Electromagnetic induction is what Faraday's law describes, that a changing magnetic flux creates a voltage in nearby conductors. So let's do more on permanent magnets. With number 2, the north pole of the magnet is located at D, because domains inside your ferromagnet point north. The permanent magnet or ferromagnet in the picture can be made out of anything except copper, because copper is not iron, nickel, or cobalt. It is not a magnetic material. In fact, if we took Cu for copper here, copper would have all paired up electrons, so it wouldn't have any residual magnetic field in its atom. Since the copper atom can't be made into a magnetic material, then it can't have domains, so it can't be a ferromagnet. Iron is ferromagnetic, but an iron skillet can't necessarily pick up steel paper clips, and the same reason my keys don't attract other objects to them in my pocket. That's because the iron has domains, but those domains don't have to be aligned. So I put 4 as B. When the 2 students drop the magnet onto the floor, they break the magnet into 2 pieces. What's going on here is that when you break it in half, and let's rotate it so it's the same orientation as the picture. When you break it in half, you can't split an individual atom. So this break makes a south pole at the back end of this magnet and a north pole on the front end of this one. So I still end up with 2 magnets. Their domains are still lined up with each other, so we still have a ferromagnet. In this case, the magnet is still a magnet. There are 2 of them, and they are not as strong as the original magnet. For number 6, the magnetic field lines take a very specific shape. They point from north to south, and notice this leaves a stronger field near the poles and a weaker field when you're farther away from the poles. On this test, you would get points for drawing both the shape with the stronger concentration of field near the poles, and points for drawing the arrows in the correct direction. The magnetic field outside a ferromagnet or permanent magnet points from north to south. So a common misconception people have is that a compass points north, but actually it doesn't. A compass points along the magnetic field line. So compasses actually point south. Think of it as the north end of a compass is attracted to the south pole. Sometimes people will think that a compass points down towards the magnet, but it does not. It points along field lines. Similarly, let's draw our field lines for a horseshoe magnet. They're going to point from north to south again. They get stronger near the poles, so we should have a higher density of field lines near the north and south pole along those lines. For number 8, a student says they have a north pole at home that doesn't have a south. But refer back to this picture. You can't have a north pole without a south because we're not splitting domains up. In this case, the domain is a solid whole segment of crystal inside this iron chunk, so that domain wasn't split apart. It still has a south and a north. And even if you divided it smaller and smaller and smaller, once you get down to an individual electron size, you're not splitting the atom, and you're not splitting the electrons in half. Iron itself is a magnetic material, and so iron itself, the single atom, is a magnet. As far as we know in our universe, north poles must have a south pole. This is sometimes called the no magnetic monopole theorem. I would pick 8C. All magnets have 2 poles because spinning electrons have 2 poles. If you can imagine this one spinning electron as having a north pole and a south pole, then that one spinning electron is its own little mini magnet. So students took this magnetic field lines and they forgot to label north and south, but we can work out the poles. Since we know the field lines point away from north, this must be a north pole. And since ferromagnets have to be dipoles, the other half of this must be a south pole. Similarly, I see field lines pointing away from this section, so this must be a north. Making the other one, because there's no magnetic monopoles, a south pole. And to double check, I know that I've done this right because I see attraction between north and south. Oh, I answered my own question. They attract each other because opposites attract. Now, at which labeled point in the diagram is the magnetic field strongest? Well, that's wherever the magnetic field has the most field line density. So in my picture, I see that the lines are closest together at point A. At point A, it would have the strongest field because it has the highest density of field lines. In the diagram, the compass points along the direction of field. So this compass must point to the right to go along with the field lines nearby it. Part 2, magnetic field for a wire. Now we're moving from ferromagnets into electromagnets, but specifically the field of a current-carrying wire. So if we imagine that we have current going into the page here, that's what the X symbol means, into the page, pointed away from your face. The magnetic field forms circles. This shape of magnet does not have distinct north and south poles, but we know that it forms circles around this wire. The magnetic field gets weaker the farther you are from this wire, but a compass would line up in circles around it. So how to do this? We're doing a thumbs up right hand rule. So make yourself a thumbs up with your right hand. Grab an object nearby to help if you need something to grab onto. Point your thumb into the page, away from your face. Point your thumb at that X like you're going to dip it into water. And look at the direction of your fingers. I don't know about your right hand, but my right hand has fingers that curl in the clockwise direction. This must mean the magnetic field travels in clockwise circles around this current. Honestly, I could have crossed out every other answer except for the last two for number 14 because none of these other directions make sense. Knowing that the magnetic field forms circles, I don't actually need to consider those other choices. Since the magnetic field forms circles, it could have only been clockwise or counterclockwise. Now let's say I take my current and I rotate it. Before it was going into the page, but now it's going left. Notice I'm still doing a thumbs up right hand rule. It's the same type of wire. When the current is traveling to the right, I still know it's forming a circle. It forms a circle, but in the direction that's difficult to draw, the Z direction. I know that my fingers are curling around this in a circle shape to make the field. I know the field is weaker the farther out I get from it. And how we picture this, because it's difficult to draw this dimension, is I'm going to put where my knuckles are. See where my knuckles are? I'm going to put where my knuckles are as my X's. This is where my fingers are pointing into the page. And if you have trouble picturing this, picture putting your fingers down towards the page, wrapping in a circle. So my fingertips touch the page when I do this. But on the other part, where I have my thumb, notice that my fingertips are pointing out of the page, below the wire. My out of the page symbol is dots. So the magnetic field travels in a circle, going into the page on the top of the wire, or out of the page below it. A strategy that I mentioned in class here, because this year you have open notes test, is take the image we started with in class. We knew this one to be correct. Our fingertips were going out of the page on the left-hand side of the wire and into the page on the right-hand side of the wire. And simply rotate it until it matches up with the current orientation that you were given. This works in this year because you have open notes. So you really don't have a huge excuse for this one. All right, so here's what I'm going to draw. I'm going to draw X's on the top. And note that you should have different field directions on each side of the wire. Notice that for this wire here, if you're on opposite sides of the wire at points X and Y, for instance, your fields point in opposite directions when you're on opposite sides of the wire. So even if you don't understand the right-hand rule 100%, I at least should see opposite directions on opposite sides of the wire. Into the page is opposite of out of the page. Now it's asking about the calculations. Question 16 is asking about how the magnetic field depends on these other quantities. And notice from down here on the right, the magnetic field depends on mu, a universal constant. It depends on 2 pi, another universal constant. The current, think more electricity, more magnetism, and the distance. Now when you're doing proportions with this equation, my hint to you is to ignore the mu and 2 pi. Now why I say that is sometimes people will be like, oh, I double the radius, so that's 2 times 2 is 4. No. The radius is the quantity that changes, the field. The 2 pi does not. So feel free to drop it or write it as a proportion symbol as you go. And let's try these out. So for number 16, if the current doubles, the field also doubles. So write this as proportions. B is proportional to I over R. So if I doubles, B also doubles. And this makes sense to me because more electricity, more magnetism. If the distance to the wire is cut to 1/3, that means you're closer to the wire, and I would expect more field. So we can do this 2 ways. We can do this as proportions. I stays the same. You're dividing by 1/3 R. dividing by a fraction is the same as multiplying by the reciprocal. So this is 3 times larger. Or we can do this from logic. If I have a point that's 3 times closer, and it's not a squared relationship on the bottom, then I should have 3 times more field. Okay, so let's walk through number 18. The pole on the right side, well, we need to figure out using the right-hand rule. This is a thumbs-up right-hand rule, and you can tell I have one variable that's curling and one variable that goes in straight lines. In this case, the conventional current is going around this coil in the upward direction. Conventional current is going in a circle. So I would use my conventional current as represented by the fingers of my hand. In my thumbs up right hand rule, I'm going to point my fingers in this direction. Imagine taking my object and trying to make my fingers match the coil. So let's see if I can do that. My fingers are going up on the coil and down in the back. That puts my thumb on the left, meaning the Hall sensor must be a south pole. Honestly, I know there's only 2 choices here. It was either going to be north or south. The magnetic field lines outside the solenoid look exactly like the ones for a ferromagnet. They point away from north and towards south. So my magnetic field is still making the same shape as it was before. On the right-hand side of the solenoid, where that Hall sensor is, has a magnetic field pointing to the left. Now we've got proportions again. The magnetic field of a solenoid depends on mu, that's the magnetic permeability of the material that the core is made of, number of coils, the current, and the compression. How close together we bring those coils. So let's do some proportions. If we triple the current, we triple the magnetic field. That's a direct relationship. More electricity, more magnetism. If we triple the number of coils, then we triple the magnetism. Because think of each little coil as its own mini magnet. So if I had 3 times more coils, I would have 3 times more magnetic field. But now here's one we probably should write out. What happens to the strength of the field if the number of turns in the solenoid is tripled, but the current is cut to 1/3? I still have the same core, so mu stays the same. I have 3 times the number of coils, but 1/3 the current. Assume the solenoid all stays the same length. So this makes exactly the same. 3 cancels 1/3, so there's no change. 1 in a proportions problem means that the field is not changed. So if I wanted to make a better core, I would want to use iron, because iron has the largest magnetic permeability. There might be materials with more magnetic permeability than iron, but one with the most permeability makes the most field. So out of this list, the one with the most magnetic permeability was iron. That's why we selected it for the core. For the last 2 sections then, we're dealing with motors and generators. The key idea behind the motor is that when you have forces acting on current carrying wires, you can make those forces turn a motor. That would turn electricity into kinetic energy. So it's important to think about forces on wires when you're trying to find the direction of force using this high 5 slap right hand rule. I want you to narrow down the 2 possible directions that force could be acting. Since the force, field, and current must be all mutually perpendicular to each other, that means if current is going to the right, that's in the x direction. My force can therefore not be either right or left. The field is in the out of the page direction. In order to be mutually perpendicular, that means the force can't be either into or out of the page. That means the force can only be in 2 possible directions. I've narrowed it down to it's something in the y direction. It is either going to be up or down, so it's mutually perpendicular to its companions. And now we apply the right-hand rule to narrow it down between up and down. Put your thumb to the right. Point the fingers out of the page. Out of the page, I want your fingers towards your face, towards your eyes. And notice that your palm is facing down. Your palm is facing down towards the bottom of the page in the negative y direction. This must mean the force is down. At the end of the problem, double check. Are those three vectors perpendicular to each other? Force is perpendicular to current, and field is perpendicular to force, because imagine field is out of the page towards you, and the force is down. Those two are perpendicular to each other. So I narrowed this down to it was either going to be up or down. It is down towards the bottom of the page. These other selections weren't even in the picture. They weren't even real options. Now, this force depends on three things. The force on a current carrying wire depends on the current, the length of the wire that's being exposed to the field, and the field itself. So for the rest of these, we're going to do proportions. If we decrease the magnetic field, then we should decrease the force. And since this is a direct relationship, if field decreases, force decreases, and we don't have to worry about any funny squares or cubes. This is 1/3 the field, so 1/3 the force. But for 28, maybe I want to write this one out because I have several variables changing at once. In number 28, we have the field is doubled, so I'm going to put in a 2 for B. The current is doubled, I'm going to put in a 2 for current. And the length of the wire is doubled. I'm going to put in a 2 for all of these. This means my force is 8 times stronger than it was originally. Remember, proportions don't give you an exact number of newtons. It gives you a comparison. This tells me it's 8 times stronger than the original force. That doesn't necessarily mean it's 8 newtons, but it means it's 8 times stronger than whatever it was before. 30 has an energy transformation for a motor. How a motor essentially works is that it has magnetic forces that push the coils of wire. So if you imagine our coils of wire rotating through this north and south pole, it runs on electricity, so the battery provides the current, the magnets provide the field, and that creates a force that moves the coil. In this case, it's electrical energy to kinetic energy, and maybe there's some heat loss. The key word for problem number 30 is that this is the energy transformation of a motor. And remember, a motor takes electrical energy as an input and turns it to kinetic energy. Just like a fan or a railgun, this runs on electricity and creates movement through the interaction of the magnet with the coil. And finally, part 5. Electromagnetic induction is where you have some sort of changing flux that creates a voltage. Well, where does this electrical energy come from? Well, you silly, you are the one moving the magnet. Your kinetic energy is able to move the magnet and coil relative to each other. Your kinetic energy turns into electricity. And so, a generator is the opposite of a motor. The magnet is pulled quickly to the left, and that induces a current in the coil. When you move it to the right, that's going to change the direction of current. So current is now going to travel in the opposite direction. But since you're moving it more slowly, that produces less current. Because there's less kinetic energy, there's more electrical energy. So it will produce less current and in the opposite direction. A way to think about this less current bit is to think of one of the two voltage equations that we used. When we were talking about electromagnetic induction, one of the two equations that we used was that the voltage created when you're entering or exiting the field is proportional to the number of loops in your solenoid, the magnetic field, the length of the wire that's perpendicular to the velocity, and the velocity itself. So going at a slower speed makes less voltage. Less voltage for the same resistance means less current. For number 33, when the magnet is moved toward the coil at constant speed, if we take more coils, each one of the coils in this picture picks up a little bit of voltage. So if I added more coils, I get more voltage. If I triple N, then I triple delta V. More coils, more voltage, more current. So here's an example of where I can use the NBLV equation. I can use NBLV when I have a coil that's entering or exiting the field. This coil is leaving the field. And so how I can increase the voltage is I could add more loops. That would increase N. I could make a stronger magnetic field. That would increase B. I could make a longer length wire, L. And I just want to be really careful here that L is the perpendicular distance to the velocity. L and V must be perpendicular to each other. Finally, I can make this go at a faster speed. So when I have 4 loops in a uniform magnetic field, I can have them all move, but they don't all have the same voltage. With this NBLV equation for induction, assume that N equals 1 for all coils if it doesn't say otherwise. So we know N are all the same, B are all the same, but L is not the same. Notice that I can use this equation, but I'm putting a star next to it. This equation is good for thinking of proportions, but I can only use it to calculate when you are entering or exiting the field. That means wires A and C that are moving to the right but not leaving the field don't have a voltage. Their voltage is 0 if they are not entering or exiting the field. That means I'm only comparing B and D. But between B and D, D has the higher voltage because D has the longer length. In fact, if you were thinking about this coil, as B travels to the right, its length is small because it's defined as the length perpendicular to velocity, whereas D's length is a lot longer for its length perpendicular to the velocity. So D has the largest induced voltage, whereas A and C do not. That's all, folks.